everyone and welcome to another video. Today we're going to be talking about stacks and queues. So these are very basic but important data structures. They kind of give you the idea of what a data structure is. So, in the previous videos you probably learned about linked list, and so linked lists kind of show you a different way of doing something you already know how to do, right? Which is to store a list of information. But the difference of the linked list was that you're able to easily and quickly insert things in the middle of the list at any time, right? Because you can just be able to kind of separate the two nodes and put one in between, right? And so that's the power of linked lists, that they can dynamically grow. The disadvantage is, of course, that trying to access specific items in the list is not a constant thing, because you no longer have, pointer arithmetic power to be able to go to any of the specific nodes, specific numbers or indices that you want to go to. So that's the pro and con with the linked list, right? But there you can see that certain applications will be better served with one system over the other. And so stacks and queues are going to be another way of organizing information. But unlike linked lists or arrays, where we're kind of doing a core concept of storing information, this is kind of built on top of that. So I haven't told you yet what they are, but you are going to be able to build a stack or a queue on top of a linked list or an array. So we kind of have to abstract ourselves from those implementations. So while I will eventually show you some code and show you how to actually implement this in a computer, whenever you first discover a new data structure, you just have to understand how it works, regardless of how you actually implement it. And then there are going to be three basic pieces of information that you're going to want to know for those data structures. And those are going to be how you insert information, how you retrieve or access the information, and how do you remove the information. And so different data structures will have different ways of managing this. And that's what makes them better at some things and worse at others. So for now, let's forget about the fact that we're programming and let's just talk about what these are. And then we can come back to that, because we have to understand the basics first before we can think about coding them. And this is how most of your data structure content is going to go when you're in Trio 2. Like when you see something like an ABL tree, you first have to understand how that thing works, and then worry about how am I going to code this. Okay, so with that said, I'm going to go ahead and start with a queue. And why am I starting with a queue? Because I think that's the one that pretty much all of us will know. If we're British, I think they use the word queue more. In America, we don't really use queue like that. We use like a line. But all that a queue is the way you wait in a line. Now, I'm sure all of you have waited at some point in your lives in a line, whether it's at the supermarket, Disneyland, or a convention center, or simply just waiting to get into some digital event or something, trying to get a GPU and going into like the waiting queue for pre-orders or something. So what is a queue? Well, like I said, you've seen it all, but let's just make sure that we're on the same page. So let me bring in some previously generated stick figures that I drew a previous semester. Actually, this was related to GPU, so GPU shortage. So you got a bunch of people lining up outside of some store, I don't know, Best Buy, or I don't know, Fry's is gone now, I guess. So yeah, so just Best Buy or Walmart or something, Target, anywhere that sells GPUs, Micro Center or something. And so what do? Well, civilized people usually don't just crowd around the entrance and then, as soon as they open the door, like stampede inside, unless it's Black Friday, right? But other than that, usually people are seen to be civilized. I remember back in the day when I got a PlayStation 3, it wasn't like the first time it released. It was, I guess, the one that came out with Metal Gear Solid 4. And I was waiting at Fry's, and I got there maybe at 6 a.m. and the store opened maybe at 7 or 8. And there were maybe like 3 or 4 people there already. And, we just naturally assumed that the person that got there before us has a right to get something before us. So if they say, hey, we only got 3 consoles, and I'm the fourth person coming in, then I shouldn't be like, yo, I want a console, because those people have been waiting longer, right? So we have this sort of innate training at some point we learned in our lives, or maybe we're born this way, I don't know. But I think we learned at some point that people that have been waiting the longer are the ones that are going to be served first, right? And that's how a line gets formed. And when there's only 4 people there and it's early in the morning, we're not necessarily standing in a line formation, but you kind of just, it's like a mutual agreement of who got there first, right? And you kind of just sort of stand around there. Now, when there's more people showing up, then you're like, okay, maybe I should get in a line because it's harder to keep track of who's where. And maybe the employees go in and help, right? But that's just all that a queue is just a line. Now, why do we care about learning queues or just lines in computer science? Well, because they're very important. Whenever you have a limited resource that a lot of things want to use, you need a way of organizing who gets to use it when. Now, what am I talking about? Whether you're buying a GPU or actually your computer using GPU power. So let's talk about CPU, because GPU has a lot of cores, etc. But like a CPU, traditional old school CPUs, you have one CPU, right? And sure, that might have multiple cores, but let's just imagine that we have one core CPU. So one core. So this little CPU has one core. And that core can only run one thread. So it can only do one thing at a time. Now, your computer, whether it's this computer or a multi-core computer, can still run multiple programs, or aka multitasking, at the same time. Even if you think you're not running multiple programs, you really are. Like, there's tons of programs running at the same time. There's services and things like that. So you're running Windows, Mac, or Linux, whatever you're running. Even if you're just on the desktop, there's a lot of things going on behind the scenes, particularly with Windows. You got Windows updates probably doing its thing. And then you got some service that is making sure that your image is being refreshed in your monitors. If you move your mouse, there's another thing tracking movement of your mouse. Another thing tracking whether you press a key on the keyboard, so there's I/O. There's probably some connection testing for like your internet, other than like Windows update pinging the server to see if there's an update. There might be other services that are checking for updates, or merely just to see if you're online. Otherwise, you get an error saying you're offline now or something. So there's a lot of things going on, and they're all different tasks, and they all need to actually do some computations to be able to do their job. And those computations can only be done by this CPU. So what do? Do you just like floor over the CPU with a bunch of stuff in chaos? Well, you could, but what if something happens like this? What if your Windows update wants to always check for updates? So it's always like hogging the CPU with computations to check updates. Then other processes can't get into the CPU and do their job, and they get what is known as starving. That's not a good thing. You're going to learn a lot about that when you get to 370, which is operating systems. But for now, this is just an example to give you an idea of why we need some form of organization. Now, there's a lot of different ways to organize multiple people or multiple processes trying to do something with a limited resource, in this case, CPU. But one of those old school traditional ways is get in a line. If Windows updates would like to get some time in the CPU and it gets there first, then we're going to give him, so say he's in spot 1 of the line. And if immediately after something with the keyboard comes in, that's going to be number 2. And so, we basically line these up in a line. And then whenever this gets served, if it wants to, go back again for seconds or something, then it's got to go to the back of the line to wait. And that basically gives it some level of fairness so that other people don't get starved out. So you can think of it like a buffet. You want to go and get some prime rib or some tofu or something, then there's probably a line for that little island, right? And you go, you get your food, you eat it. When you get more, you got to go back in the line. The buffet thing is kind of dated now, although the buffets are gone post-COVID, so it's kind of sad, but yeah. Anyways, that's the idea of why queues are important. And so it makes sense to know how to program one and how to actually understand how more than just to program it, understand how it works so that you know when it can be useful in your own projects. So let's talk about the different operations that you can do in a queue. So again, these data structures have those three core things: how to insert data, how to retrieve data or access data, and how to remove data. And the reason why retrieve and remove is different is because retrieve is more of like, how do you find the information in there? There are certain rules of what you can and can't pull out. And then the delete is more of like just completely remove. Okay? So it's like, think about like a book, a way of writing into the book, a way of looking up something in the book, and a way of removing something from a book. Different processes, right? You need to be able to find something before you can remove it, sure, but you don't need to delete something to just find it. However, certain data structures might have that requirement, such actually as a queue. So let's go ahead and write out some of those operations. So in terms of inserting information in a queue, it's called the enqueue. And then to remove information from your queue, which also happens to be the way you access or retrieve information. So here, I guess they combine the access and delete into one, which again, not all data structures do, but queues happen to do, is called the dequeue. And those are really your only two main components of a queue. You might also have additional operations that you can do in the queue, but like this is like the purest version of the queue. It's just to have these two things. You put something in and you take something out. Now, what does it mean to enqueue something? Okay, so a good way to remember what a queue does, by the way, and also to kind of understand it better, is to know what the FIFO acronym stands for. And that actually stands for first in, first out. Now, you might have heard the phrase first come, first serve, in places. Again, that's the idea that the people that have been waiting the longest or that got there first should get served before the people that have been waiting less or that got there later, right? Both of those things mean the same thing in a way. And so what that means is that whenever you have a new process, a new person, a new item that wants to enter your queue, you're going to enqueue it. And what that means is you're going to throw it into some sort of line or whatever's holding your line, which hence is like an array or a linked list, and then basically just have them wait. And then the dequeue process is that when your resource is ready to have somebody use it. So like, let's say your CPU has finished the previous task or has run out of time to do the previous task and now can take the next one. Then it needs to ask someone, hey, send me the next task, and then it has to figure out who to send, right? And of course, if it's using this queue property, then it's going to be the person that's at the front of that queue. So let's talk about what front means. So front is a term that is used in queues, and also we have the term back. Now, I think these are also pretty intuitive, but just to be safe, what I mean with front and back is that the next person or the next item to be served out of the queue is going to always stand at the front of the queue. So whenever you dequeue something, which means remove something from the queue, you're going to dequeue whatever is at the front of the queue, aka whoever's at the front of the line. Pretty straightforward. Whenever you're enqueuing something or you're inserting something into your queue, so someone joining the line, where do they join? At the back of the line, right? You're like, hey, where's the back of the line? And they're like, it's over there. When you see this massive line and you're like, whoa, that's a big line. AKA Disneyland or something, right? So yeah, front and back, important terms, and also useful when it comes to enqueue and dequeue. Two more terms that I want to bring out, but they kind of mean the same thing in a way, is top and peak. So top is more of a stack term, but I want you to just be aware of it in case you hear it. And also peak is a term that's not really part of your normal queue, but it can be. Peak allows you to see what else is in the queue. So normally, the only things that you can see in the queue is when you dequeue something. So if you want to remove something from the queue, you get whoever's at the front. And then that's it. You either serve them or that's it. They got to go back. You can't just put them back in the front. So like, imagine you're at the DMV and then you get your number called. And then that's also a queue, by the way, or at least you hope it is. and then they get to the person, and the person's like, "Oh, wait, you know what? Never mind. It's my lunch break, so just go back to the front of the line and wait for the next time to be called." You can do that in the real world. Uh, I think people see you around that will probably understand that, but you might also get yelled at by someone who might think you're cutting the line, right? So normally in like a purest version of a queue, once you get pulled out of the queue because it's your turn, you can't just go back to the front. You got to go back to the end of the line. Now imagine if that was the case here, you'd be like pissed off, especially if you've been waiting for like an hour or something. You're like, I'm sorry it's your lunch, but like now I got to go wait like an entire another hour for a mistake that's not on my end or something, right? Well, okay, relax. But yeah, technically that's how like a pure version of a queue would work. And so you may not want your queues to work like that, so you need to find out, you'll have to add extra features to your queue. But in the most basic case, that would be the way it would work. Once you get out of the front, you got to go back to you want to re-enter the queue, you go to the back. Peek is like trying to see who's like second. So who's after the front person. So like if I peek whoever's peek 1 would mean like peek the person that's behind the front, or peek 2 persons behind the front. Like who is like this gonna get served after the person gets served after the person at the front. And top is kind of the same thing. If you say top is like who's at front, top 1 who's behind the front, and top 2 who's behind that. Okay, so those are just some terms that you'll run into when it comes to queues. And again, if this is the actual queue, this person gets in, gets a GPU, and leaves happily, and the queue moves forward. And then this person gets in, gets a CPU or GPU, gets happy, and the queue gets forward. So this is the DQ process when he goes in the store. Let's say this guy's a scalper. So he's like, I'm gonna get back in the line to get a second GPU. Ha ha ha. So when he goes back in the line, he NQs, but he goes to the back of the line. So this person goes in, gets his DQ'd out of the line to get a GPU, and goes home happily. This person gets in, and then they're like, oh, we're out of GPUs. That's it. It's over. So he goes home empty-handed. No, let's say he got a GPU also. And now the scalper's back, and unfortunately, he also gets a GPU and goes. But technically, he was only able to do it after the other people that were in the line got it. So there's no scenario where, before he did that, he gets one GPU and then goes back into the front and gets the second one. No, it's still fair in that sense. So at least the people that were waiting in line got it, even though the scalper got 2 of them. Oh well. Anyways, that's it. That's all there's to it, to a queue. Now let's talk a little bit about how you would implement a queue in programming. So the 2 main ways that you can implement it now that you learn how to use linked list and how to do arrays is using linked lists or arrays. So let's talk about implementing it using a linked list first, okay? So what we have to implement is the organization of what gets queued, when you NQ that it goes to the back, and then when it gets DQ, get something out of the front, and basically code those 2 operations along with being able to keep track of who's in front and who's in back, so that we can code take the person out. So linked lists are really kind of nice for this, because the advantage of linked list again is that they can grow dynamically, right? So you can already see how this might be problematic with an array, because with an array you have to pick a size for the queue. So it's like saying our line, it's kind of like real world, even if you go to Disneyland, there's probably a limit in the amount of people that a line can hold, unless they do like an extension to like an overflow, they call them, I think, right? So it's a real world issue that you have to figure out, how big should I make my queue? It's also wasteful in a way, because imagine on like a really busy day, sure, you get to use all that line space at Disneyland. But like, imagine that there's like a not so busy day, like low season or something, in the morning, like early morning, where the lines are small-ish. Technically, they're wasting a lot of empty line space that, I don't know, could be put into a new ride or something, right? But they can't do that because they need to have the space available for when it's like peak hour or peak season. So that's the same thing with computer, right? When you make an array, sure, you want to make it as big as you need to in the worst case scenario, but in everything but the worst case scenario, is going to be wasteful. With a linked list, you can grow and shrink as needed. So that's like the ideal scenario for a linked list. But I'm going to show you the linked list version first because that's probably the better one. Okay, so remember with the linked list, we have two components. I mean, we could make it a doubly linked list, but that's like overkill. Single linked list will work just fine, unless you really want to do something with the peek function. But we're just going to make a basic queue. It just has two main operations, and we'll call it a day. Oh, by the way, another thing that's also useful and not technically part of it, but kind of important to have, is a size, right? That keeps track of how many items are currently in your queue, so how many people are waiting in line. Particularly important for when you're doing an array implementation, because then you can actually you can find out if you're at capacity or getting close to capacity, so you can resize your array, or simply say, hey, the queue's full, come back later. But for linked list, it's not as important, other than the special scenario of trying to remove something from an empty line. So what happens when your line is empty and the DMB person says next? Does your universe crash because it doesn't expect that to happen? Or does it just simply nothing happens? So with programming, you have to always plan for those things. And if you try, it's like trying to remove something from an empty list. It's probably going to be a null pointer exception. So you got to be careful about that, but you can check for null in the case of linked list. But with the case of arrays, there isn't really much you can do other than probably going out of bounds with a negative number or something. So size is useful to avoid those scenarios by checking if the size is 0. It means that your queue is currently empty, so don't try to take something out from something that's empty, because that will not end well. Okay? So, all right, linked list node. We got data and link component, singly linked list. And so what I'm going to do is I'm going to keep track of 2 pointers, which are conveniently my front and back. I'm just going to abbreviate them to be B for back and F for front. Now, this is slightly counterintuitive, the way you code this. Because the intuitive way, or the wrong way to code this, would be to make your linked list like this. So, when you think of like a line, you typically think of facing the front of the line. So you might be compelled to say, I'm going to code my queue by making the back where my head pointer would be, and then making the front where my tail pointer would be. And it looks kind of nice because the arrows are pointing towards the front. And it's very easy to add something to this queue, because all you got to do is say, okay, if I want to add something in, so I got a new node or a new person that's going to join the line, he just basically goes to the, whatever the back pointer is, copies that over so that it puts here, and then moves it back over. So inserting is not a problem, and queuing is not a problem. Dequeuing is a problem in this scenario, because if you want to dequeue someone, you're like, oh, well, the F is pointing to it, the front is pointing at it. Oh yeah, cool, all right. So you can remove it, but now what happens with this? You got to make it point here, and also you need to change this pointer to point to null, because right now it's still pointing here like a dangling pointer. So what do you do then? You're like, well, I guess I can, traverse the entire linked list to move that pointer, so I can go in here, go through all the pointers until you get to the end, and then now that we know that's the new end, which I guess we have to make sure we know the size, so we go one before the end, or do the thing where we keep a pointer next, so when we see pointer next being null, that means that we're at the last node. We can do something like that so that we can then change the front, but it's inefficient. And so remember, with data structure land, you no longer just care about getting things done. Now we care about not just getting things done, but also doing them efficiently. And what do I mean by efficiently? 2 main components: space and time. Space and time are important in everything we do now. Why? Well, for starters, we don't have all the time in the world, at least, or so we think. So we want things to finish as quickly as possible. So time is important. Traversing this entire linked list takes time. Now you're like, oh, it's like a millisecond. Sure, it's a millisecond in your specific scenario, but it's actually dependent on the size of the list. get a big enough list in here, and it's going to take a long time. In fact, you could make a list long enough that it will take hundreds of years to just go through each pointer. Now, that would be a massive list, though. But still, it's not going to be instant. And if you're doing this repeatedly, you're just unnecessarily slowing down your code. And we care about that because most of you, when you go in on your internet at home and you want to check your email, you want the stuff to be done like that. You don't want to have to wait 2-3 seconds each time because that adds up over time. And if you got to check 10 different emails, that's 30 seconds wasted potentially. So yeah, not cool. So time is a big issue. And space, why is space an issue? Space is not as big of an issue nowadays as it was 30 years ago or something. Because I mean, fortunately, we're lucky that space constantly keeps growing in terms of available space, but not, think about hard drives. Now we have 18 terabyte hard drives, that are normal hard drive size. When before, the biggest hard drive we had was 1 gigabyte. And we were like, whoa, it's a gigabyte hard drive. That's hardcore. So yeah, I mean, that's good. And prices have gone down for space. So that's pretty nice. But time, the only way you get faster at things is by building a faster processor. And when you take 219, you'll find out that unfortunately things are becoming harder and harder to make faster, at least at the rate that we were doing it in the past. So now that's not to discredit space, but what I'm trying to say is that they're both important. And in this case, how do we gain space? Because the linked list version can grow and shrink as needed as our queue grows and shrinks without wasting additional space. Whereas the array version definitely would. Or if we make it one version where every time we add something to the queue, it's full. And when we add something new to the queue, we have to resize the array. And then make a brand new array, copy everything over, and then use it. And if something gets dequeued, we delete something from the array and copy everything over to the smaller array that we made. That's also really slow in terms of time. So time and space, big things, right? So we don't want this. We don't want this we have to do the whole traversing of the linked list just to dequeue something. So how do we solve this? Well, the solution is actually easier than the explanation to build up to the solution was. All you do is you flip these pointers. I didn't want to just start out with this because I wanted you to understand why we did it this way and why it's important to think about these things when you're creating these data structures. So that's the merit behind that. But yeah, if you flip this, the problem is solved because now we can do constant insertion and constant removal time. So that constant NQ O of 1 time complexity and constant O of 1 time for the dequeue process. So let's do that. So let's go ahead and enqueue something. Now in the past we were able to enqueue constant as well. That will not have changed now. So if you want to enqueue something, we send it to the back of the line, right? So we have a back pointer that's pointing already to the back of the line. So we just throw it in there like that. Now, after we do that, we just say back next gets back. So we update the pointer, bam, done. So insertion at the end, no problem whatsoever. So our enqueues are all good, but they were good with the other method before, so no gain yet. The gain is going to come from here for the dequeue process. So when the next person gets served, we're able to just look at the front pointer and remove him that way. And if we want to be able to access and update the front to be the second person in line now, all we do is say, since the front's currently pointing here, we say front next gets front, which basically makes it point here. And then this gets served, so it's gone now. Bam! You can see there's no traversals required. It's constant time. This is what we want. This is good. So that's how you enqueue, and that's how you dequeue. All right, so that is going to be your linked list implementation, basically. Let's look at the array implementation. So array is going to kind of bring up the issue of space that I brought about earlier, but let's just forget about that for a second and just assume that we're always going to have 6 or actually let's do 8 because I have a picture with 8 already from last semester. So this is that one. Save these from drawing stick figures, but yeah. So suppose we have 8 things that we want to store in our queue, right? So we got people. Okay. So you might be like, oh, okay, I only gotta store 8 things, so I'm gonna go ahead and make an array of size 8, because in theory I should be able to hold up to 8 things. Oh, this person lost its slide in the array, right? Sure, that's fine. But you can hold even more people technically, right? As long as at one time there's no more than 8, you're good. But like, if 3 more people show up, as long as they're not all waiting at the same time on the queue, then in theory you shouldn't have an issue with this, because the queue is more like a capacity at a given point. It's like Disneyland, right? So let's say that like the Rise of the Resistance in Disneyland can hold like 2,000 people in line. That doesn't mean that in one day it can only have 2,000 people in the ride. That just means that at a given point in time there couldn't be 2,000 in the line. But given the fact that the ride is operating and people are being constantly removed from the queue, they can be filled in by new people coming in. So, if you can serve 1,000 people per hour, even if at some point your line gets to 2,000, as long as it doesn't grow beyond that, we don't, turn people away. If at some point there's like less flow of people, the line can go down to like 1,000, and then kind of reach equilibrium in terms of people coming in and out. So for the full day, you might get 20,000 people in the ride, even though you could only fit 2,000 in the line, right? So I hope that makes sense as to the why your queue should be able to, even if it's a given size, should be able to process more than the size of the queue, as long as not everybody at once just decides like, I'm going to go to this ride at 1 p.m. and the whole park decides to do that, because that's when you hit those capacity issues. And then you got to think about resizing or overflowing your line, or simply saying, sorry, the line is maxed out, come back later. So yeah, let's again, there's 2 ways of doing this. I'm going to show you first the bad way of doing it, and then the good way. So the quote unquote bad way is we make an array of size 8, and we also have our back or front. I'm going to call them pointers, but they don't technically have to be pointers. They can just be indices, like numerical indices that store where they're pointing to per se. But you can make them pointers too. Like, that's not a problem. At the end of the day, remember, this is all pointer arithmetic. So addresses are just the size of the type shifted +1, whatnot. So yeah. Okay. So we have an empty queue, and that we have to figure out what the front and the back is. So in the naive way, I'm going to go ahead and say that the back of the queue is going to be I'm going to put it at 0. And again, I'm doing this the wrong way, so it's kind of I'm tempted to make it right. So yeah, we'll just make them both point to the same spot. Okay. So let's say a couple of people come into the line. So we got one person, early riser for the Rise of the Resistance. So he gets in line there. And then the second one comes in. And then your back, you can keep it pointing to the last person or to the next available spot. So in this case, we're just going to say next available spot. So the next person comes in. So he goes to wherever B is pointing. So we point it there. We shift it by 1. Another person comes in. And then the ride starts working. Okay? So the ride starts working, and so we get one person that gets removed. So he's like, yay, I got to ride the ride. Goes to other rides or something. Now F moves back to point to the next person that's ready to go. This is one way you can do it. Another way you could do it is you could shift everybody, which is more, I guess, realistic to like a real world representation, right? Because like when somebody gets out of the line at the front because they got in the ride, the line like slowly shifts, right? So that we have the like slowly creeping of the moving of the line, where you're like standing and then like it moves a little bit and you stand again and move a little bit and stand again. That is like, I guess, nature's way of shifting everything so that the space at the back of the line opens, right? Because what you have essentially is a little space at the front from the people that got in the ride, and that space needs to transfer itself all the way to the back. It's pretty cool to see it. Like, if you ever look up some pictures of like some sky view of a line and how that movement works, it's pretty neat to watch that. But anyways, so you could do that, and there is a there is an advantage to that, but I'm going to come back to that. I'm going to make it the version where you don't move stuff. Because remember, moving stuff is an expensive operation. Copying is expensive. So if you don't move it, hopefully you can already see why this will be an issue. But let's say we got a couple of more people coming into the line. You know, we got like a family. All right. And now it's been slow morning. We got some people coming out. So we got this person that gets served. And this person that gets served. Oh, he just literally ripped off the little line thingy. Okay. So yeah, we just keep adding more people in. So maybe you get one more person in. Maybe one more person comes out. And now you're going to see something that's going to happen here. So we get one more person in the line. And now one more person wants to join the line. And even though there's space up here, there's no space for him. So he gets turned away. You're like, but like, look, there's so much space in the line. Like, make these people move forward. You're like, nope, sorry, we don't do the moving forward here. We're a non-moving line or something. I don't know. So yeah, problem here. And what's the problem? That you're wasting space. Even though your line can hold, you're wasting space. So right now, until now, I mean, like, inserting and removing was constant time. But when you run out of space, you have two options. You have to either shift everybody at once or resize the line or do something, because now you are out of space, even though the line can hold more. So you can see why this is wrong, right? I mean, like, hopefully this is pretty obvious as to why it's wrong. What is the solution to this? Okay, well, before I show you that, let me show you the sort of not so good solution to this. The not so good solution to this is kind of how, what we do in terms of real world, I guess. Because that actually works out in the real world better, but it doesn't work out as well for computers. And that is, oh, please don't decapitate stick figure. There we go. That is going to be that if we have people coming into the line, so restart the scenario basically. So restart the simulation. And then this person gets served. You can't go in, you know, run a for loop that runs through every single spot and shifts everybody forward, right? And then we get two more people coming in. And then one person gets served. And now we got to shift everybody forward. So why is this bad? Well, time. Each of these is a copy operation. That means that if you have a line that's full, so like let's say this is actually full and then one person gets out of the line, you have to make basically 7 copies, right? Because it's size 8. So you make if you think of n as the size of the array, you basically have to make n minus 1 copies. That takes time. That's not efficient at all. That is not efficient. That is not constant. That is linear time. Bad. So not good. Not good. It's really this is like really worst case scenario. Like you got so many copies that it's like really bad. So anyways, that's why this won't work. So, but this is what we do in real world because it just works. I mean, like people in line have nothing better to do, so might as well make them move. So what do we do instead? Okay, well, in the terms of computing, the best way to approach this, other than using a linked list, is if you're back to the scenario where your front is here, then you put somebody in here. What you do is you wrap it around and they enter here. And now your back is pointed there. So you think of this as not a line, but a circle. Okay? So let me draw that to make it easier to visualize for you. Very high-tech circle, right? Okay, I don't know how many. 1, 2, 3, 4, 5, 6, 7. That's it. 2, 4, 6, 8. Okay, all right. I think we got it right size. So your circle, I mean, in computers you can't do circles. You can't even do multi-dimensional arrays. Everything is flat because RAM's flat. But you can think of it like a circle. by wrapping around. So we got a stick figure in spots 5, spots 6, and spot 7. So now, when we inserted this stick figure, what we did is we basically put somebody here. And you can think of this as the front of the line and this as the back. So it's kind of like it's going clockwise, basically, like a clockwise clock or watch or something, okay? So yeah, if I want to put somebody in the line now, they go here, and then this keeps shifting, which is the equivalent of putting somebody here. If somebody is going to get out of the line, which is the DQ process, then he gets out, and this moves to the next person in line, which is the equivalent of taking this one out and moving him here. And so on. So like, let's say we put in 2 people in the line. This moves here. This would be the equivalent of putting in, well, hold on, I need more humans, more stick figures. There we go. And then here we go. So you can see how it's kind of like a circle that's spinning, right? So that's the idea. And so using this neat little trick, you can maximize your usage of space in the queue. Now, you still can't get out of the situation where you run out of space because you max out your line. There's no way around that. But at least this way, you can use the line that you have at capacity at any given moment. What would this be the equivalent in like a real world? Well, this is kind of weird to visualize, but I suppose you get a bunch of people in the line, and then somebody holds like a flag, which represents the front, another flag that represents the back. And so whenever a person gets out of the line, they pass the flag for front to the person behind them, and then that space is available. And so if you got, whenever somebody wants to join the line, they go and look for the person with the back flag, and they join next to them. And so it's kind of weird, and it would be very difficult to work out in a scenario where like they're basically next to each other. So like, if we could have a scenario like this, right? And this point, front and back are pointing to each other, but the line is actually full. So you definitely have to have the person at the back hold the flag, the last person. Otherwise, like the front and the back is being held by like someone, which is kind of weird. And also, I suppose in like real world, this might be prone for like people sneaking in the line or something, and be very confusing to keep track of. So for humans, let's just make them move forward when it's their turn. But for computers, this works perfectly. Okay, so it's kind of round robin sort of looking thing. Okay, so yeah, this is known as a circular queue, and it's the best way to implement a queue as an array, because you maximize that. Again, you'll still run into problems if you try to, if you're at capacity. So what do you do actually if you're at capacity? 2 things. You can just say, hey, line's full, or you make a bigger line. Now, when you make a bigger line, again, this is being stored as an array. You have to be careful about that. Let's say you're in this scenario and you want to make the bigger line. So if you make the bigger line and you just simply say, oh, I'm going to make it, I don't know, let's just, you probably want to make it twice as big, but let's just say for now, for simplification purposes, I'm going to make it 2 spots bigger. Okay, so you might be tempted to say, oh, well, hold on. To properly visualize this, I want to do this. I'll take the old one and the new one, right? And then I want to make this empty. I can't get rid of the head there. There we go. Okay, so we got a bigger array and a smaller one, right? So we allocate the new one. Now we got to copy stuff from the old one. Now you got to be careful here. You can't just do like a for loop and do like what would be like a usual deep copy, which is you just do like this. And then you end up with do all the copy over. And remember, your front and back is currently pointed by the same spot. Now, why can't you do that? Because if you try to insert an additional item here, because you are going to, I mean, that's why you had this issue, because you were trying to insert one more, he'd go here. And then this would move over. Well, actually, no. He would try to go wherever back is pointing to. He'd probably either override this, which would be an error, or he'd go here, in which case it's going to look now, it's going to mess things up, because now this is front, and then this person who just came in is going to be second to front. It's a mess. Like, this won't work. There's gaps. So that's very problematic. So you can't just do like an easy copy and be done with it. You will run into problems. It will not end well. The best way to do it is just to dequeue everything from one queue, and as you do that, enqueue it to the new queue. Meaning that since this person is next, he'd go here. So in the new one, it doesn't really matter where you start, but just pick somewhere. And then just throw them in. You can put them in at the beginning. You can put them in elsewhere, whatever. Just pick something else wherever your front is. And then just start throwing people in like that. So when that gets dequeued, this wraps around to here. And so this is dequeued and then queued there. Dequeued and then queued there, and so on. I think you get the idea, right? So just make sure that you do that. Build a bigger one, dequeue everything from one, and then queue it into the other one. Otherwise, you're going to mess up the order. Okay, so that's the only thing. Like, everything else is pretty trivial here, particularly when you're coding it, with that exception. If you don't do that little bit, things are going to get weird, and you won't find out why for a while, and it's not fun for anyone. So yeah, that's all there's to it. That's a queue. Coding it, like I said, I mean, with linked lists, it's just a matter of like modifying your traditional insert and delete functions there and calling them enqueue, dequeue, and I'll show you some examples of that. And then again with the array, you want to make a circular array as your implementation of it, and just keep track of this stuff with the front and back. I guess one trick here when you're trying to wrap around is you just check the size of the array. If back is pointing to out of bounds the next time, or the size of the array basically. So like 8, size is 8. So if your index is currently 8 and that's equal to the size, that means that the next thing you insert is going to be having to be put around, like it's going to have to wrap around. So if that is the situation you're in and you're trying to insert something, then instead of making it point out of bounds, you can make it point to 0. So you can just do an if statement for that, or another trick is you can use modulus. If you use modulus, you will never have that issue of going out of bounds, and it'll easily wrap around. The only thing you got to keep track of is to make sure that you don't, if your queue is full, that you don't take additional things, because they will overwrite, and then you can call resize, etc. Best way to keep track of that is to keep track of where front and back are pointing to. If they're pointing to the same thing, then that's a flag that your queue is currently full or it's currently empty. So just keep track of which one of those two scenarios it is, and then they should be good to go. The best way to find out which scenario it is to know whether what you have is there is valid or not. So yeah. Okay, moving on. Let's talk about the other data structure that was up there, and that is stack. So you've heard me use the term stack when talking about memory, like call stack, stack or heap in RAM, and those kind of things. And it turns out that they're called like that because they are using a stack data structure. So what is a stack data structure? A stack data structure is kind of like a queue, but the way things are inserted and removed is different. Again, I told you data structure differences between all of them is just how things get inserted, removed, and retrieved. Of course, they're going to be different. Otherwise, it would just be called a queue. But how are they different is what makes it unique. And so instead of following that FIFO, first in, first out, first come, first serve approach, it uses a LIFO approach, which is a last in, first out approach. So for this one, I got a couple examples for you. I'm going to just throw as many as I can. Maybe one of these will resonate with you and you'll understand it better. But the basic idea between behind the stack is that the last thing that gets stored in there, that gets inserted, is going to be the first thing that comes out. So this does mean that the first thing that comes out, that comes into the stack, is literally going to be the last thing that ever gets pulled out, because this kind of gets hidden in the back. So the examples of that is, for example, is in a grocery store. So typically now all different grocery stores are going to do different things. Some of things will be queues, but let's talk about like the dairy department. Okay, so most of those perishable items, dairy or meats or whatever, they tend to put the freshest ones in the front. Sometimes not, because they want to get rid of old stock before the new stock. But in some cases, they do want to put the fresh stuff in the front, and they do that because these things are diagonal. So, like for example, I go in here and I'm gonna put this carton of milk or whatever in there, okay? And so this thing is like springed or gravity based, and this thing expires, I don't know, like June 10th, and today is June 1st, or I don't know, whatever. Doesn't matter. If I come in with a new carton, it's a weird bottle representation, that's fresher, I'm gonna push this one up to put this one here. So if a customer comes in and how did I do my stick figures last time? Here I got an army of them. The clone army of the Republic. So if we got a person coming in, he's gonna grab a cartoon of milk. He's gonna go home to drink milk. Then this one comes out, right? And then, he comes in and grabs it. Or hey, it could be GPUs too. And he takes it, right? And then this one comes in and is like, hey, there's no milk. Okay? So he maybe waits or something. And then eventually, they come in and restock the milk. And they put in a couple of milks in there. So that one came in first, and then put another one, and another one. The last one that was put in was this one, which happens to be the same one that the next customer is going to take. So that's the basic idea of the stack. So the last thing that was put in is always the one that gets taken out. And that does mean that in a scenario where like you have a really high, like top tier customer service, like people at the supermarket who are always making sure that the inventory is stocked, and they always have like stock to stock it up with, it's possible that like, a bunch of people are coming in and day out to get their milk, and like, maybe there's milks here. This person comes, takes milk, proceeds to go, and then the employee's like, there's a spot of milk left, let me push everything in and put it in there. And so it's possible that like, everybody just keeps grabbing the front milk because it's the one that's available, and it keeps getting restocked, and these two milks back here are just gonna wait there forever until like one day the restocker wants a vacation. So he just, or just is late at work that day, okay? And so because it's late at work, people actually come in and grab milk. And then finally, like these two that have been storing for like, I don't know, like 6 months come in. This person grabs the milk, goes home, tries to drink milk, and is like, yo, this thing is like spoiled. Or like it expired like 6 months ago. We're like 2024 and this expired in 2022 or something. So he tries to drink it, and then he's like, oh no. Well, hopefully he sees the label, because otherwise he's going to be like, and he dies. Rip. And then, same with this one. It's like a time bomb, right? So you can see why a stack can be problematic in this scenario, but usually it's good because it allows you to get the freshest milk. So all these people are like, wow, this store is always good with milk, and so on. Okay? So that's one example. Let me give you more examples. Let's talk about the buffet example. came up with it a couple of years ago. Again, now it's kind of outdated because buffets are kind of gone. But like, this is I think an actual practical one, or at least it used to be again with buffets. The little plate servers things. So when you go to a buffet, you grab your own plate usually, and so they have these little like locations where the plates are kind of in a hole, and like it's like spring based. So like when you go and grab a plate, so if I go and take this plate, the spring pushes up, it like uncoils a little bit and pushes up more plates, right? And so whenever they come in to deliver more plates, so like let's say I'm coming, restock person, he was fired from supermarket because he was late that day, so he got a job at the buffet now. So he comes in, and he's like, he's really good at his job, so he just happened to have a bad day that day, being late. But yeah, he comes in and he stocks more plates in here, compresses the spring, brings them down. Again, people keep grabbing plates. So these are plates that have been taken. And then, workers like, yo, I gotta put in more plates, more fresh plates. And that's good. In like the buffet scenario, it's good because the plates are warm and cleaner and stuff, right? They haven't been like floating around for a while. And so you're always getting the cleanest plates available. But the important to say cleanest plates available. So again, our, really good employee decides to, take a day off. And then the person that was going to cover him is late that day. And so people come in that day and they're still grabbing plates. And finally, they get to the ones at the bottom that have been there the longest. Again, these plates have been there for like 2 months. And they're like, they should be clean, but I guess imagine they're like moist in the air and like moisture gets in and there's like fog, what do you call it? Not fog, moss, like fungus grows on them. Okay, so there's like fungus. Person eats it, also joins the rip land. Okay. Now, hopefully, this guy didn't get fired though, at least, because it was the other person, right, that was gonna cover him. So he's like, "Ooh, dodge that bullet." So yeah, another scenario. Again, you're all now making it sound like stacks are really bad because they cause all these griefs, right? But no, they're good in the sense that like. They allow you to be able to access the newest information stored. Let's talk about computer science, where I guess a stack's actually a good thing. Okay, so main memory. Main memory, you have two types of memory. You have the heap and a stack. The stack usually holds all the static variables that you make in your programs, and then the heap is like the dynamically allocated stuff. Now, how do you store two types of memory in what is essentially a 1D array? Well, you could say, all right, I'm going to split it in two and say this part is for the stack and this part is for the heap. Okay, sure, that'll work. But the problem with this method is that if you have a program that's really stack heavy, so nothing's dynamic, everything's static, you only can use at best half of the available memory, right? Because the other part is reserved for the heap. So even if your program doesn't use a lot of heap, it still can't take advantage of that space. By the other hand, if everything is dynamic in your program and it uses all heap and like very little stack, except for like the pointers, and even the pointers, like if it's a linked list, you only restore 2 pointers. So like, yeah, you wouldn't be able to take advantage of it either. You'd only take advantage of half. So there's no easy way. Now you could say, okay, well, I could just make it everything be heap or everything be stack. Sure, you could do that, but then again, what if you want to use just a little bit of stack and a lot of heap? Like you don't have that flexibility, right? It's fixed. The sizes are fixed. So while there's different ways that you can solve this, one nice and elegant way is to actually use a stack data structure. What's the cool thing about a stack? Well, look how it grows. It grows from a starting point, it grows outwards, right? And the more things that are in it, the bigger it gets. And when things get removed, the smaller it gets, but the origin stays the same, right? Well, that's perfect for us. Because guess what I can do? Instead of having these be fixed sizes, I can say this is going to be, I'm going to start addressing things from here are going to be heap memory. And then stuff starting from this address is going to be stack memory. And the cool thing with this is if I have a really stack heavy program, this thing can grow all the way here, and this can be the top of it. And if I have, if the heap is not using that much space, then it doesn't cause any problems. Whereas I couldn't have done this distribution in a 50-50, like hard-coded space differences. By the token, if I have a really stack heavy program, or sorry, heap heavy program, I can use more than half and not have any issues as long as I am not using too much stack. So by using the stack data structure, basically having two stacks in there, one going from here, one going from here, I can basically go like this, right? I can still go 50-50. I still probably end up having a lot of space. So like what if happens if a program uses very little of both? That's fine. Uses some of this and uses some of this. No problem whatsoever. The only problem I'm going to run to is a problem that I wouldn't run to in any other scenario where I have too much of both. So like maybe I have this much of this much of heap and this much of stack, and then bam, right there. Stack overflow. Because I ran out of space. But that would have happened regardless of any organization methods you would have used. Unless you said like, hey, this program is just not allowed to use any stack. But like, you needed the stack space because it's being used. You needed the heap space. You just ran out of space in general. So yeah, using a stack allows you to have the flexibility to be able to maximize your memory usage of the two types of memory in scenarios that otherwise wouldn't have been possible if you have just said like, hey, I'm giving half to this and half to that. Or I'm giving always a quarter to this and 75 to that. Sure, but what if there's a scenario where you actually need it about 50-50? That wouldn't work. This is dynamic in the sense that it can grow and shrink as needed be. And as long as between both combined, you're not using the entire memory, you're okay. The moment that you do, that's a different problem that you should have solved. Buy more RAM. Download more RAM from the internet. So yeah. Okay, so that's, I guess, a positive example, non-death resulting example of using a stack. But there's tons and tons out there. You can go on Google, like, what is a stack useful for, and probably find out a bunch of different places and things where it can be used. But yeah, the Q wouldn't have helped you out here either. So like, stacks is just the way, it's the meta. So you'll learn more about this stuff when you get to 219 and 370. But yeah, so let's talk about the operations that you have in a stack. And you've seen things like inserting and removing, but these have a special name. And those special names are push and pop. And just like the queue, you have the concept of a top, and you have the concept of a peak, and I suppose you should have a size as well that keeps track of the size of the stack. Again, you don't want to remove something from something that's empty. So like an empty stack, and you're trying to remove something, that would give an error, right? So you would know not to do that because you checked that the size is 0, and you're like, oh, it's empty. Similarly, if you're working with a stack that is full, how do you know that it's full? Well, you can look at the size of it and see if it's full. So far, again, I haven't brought in how you would implement a stack using a linked list or an array. That's, again, we're just trying to get the concept first before we actually go in and think about how we actually would implement this. So push and pop. So again, the three things that you always want to do for your data structure, and by do I mean define and understand how they work, is your insertion, your deletion, and your access or retrieval. By access or retrieval, I'm saying it goes by both names, okay? So in this case, push is how you insert to the stack. So like push it inside, I guess, and then pop is like pop it out of the stack. So pop is, again, kind of like the duo, where it does both access and delete. And then top is another way that you can look at what's at the top of the stack, meaning what's the next thing that would have been pushed. So you can think of like the front-ish. And then peek is, again, to like look who's behind. But again, those are not traditional in the sense, in the purest version of a stack, you got those two operations and that's it. So yeah, I mean, if you are, that's all there's really to it. Like, if you got a stack and you got a bunch of numbers in here, well, let's just forget about numbers. Let's think about queues. Okay, so I'm gonna build a stack. I'm going in and I put it in like that. Boom, I got one thing in my stack. How did I do that? I pushed into the stack. Next, let's push something else. All right, so let's push this square into the stack. And the top is usually always pointing to the next to the next thing that would get removed from the stack. So let's push in one more thing. So push that. Now it comes the time we want to remove something from the stack. So we pop from the stack. It takes out whatever's at the top. So this one. So this gets thrown away. Moves here. So we push another one. Push that in. Okay. Now we're going to pop. So we're going to pop this out. So pop again. Pop again. We don't pop again because now we're empty. That's all there's to it. So yeah, I think that's as much as I want to say there. So obviously you wouldn't want to use a stack for something like Disneyland because that means that everybody would literally cut in front of you as they show up in the line. But you would want to use it for things like your RAM. So you can see where certain data structures are good for certain things and not for other things. So yeah. Let's talk a little bit about implementation now. So you can implement the stack with both an array and a linked list. The same sort of pros and cons are going to come in that they did for the queue. The stack linked list implementation is going to allow you to basically be able to resize, to like have your stack grow as needed be without having to resize actually. So no worry about resize. So the array version, you have to give it a size, and if it gets full, you gotta copy it over. At least the advantage with the copying over the array one is that you don't need to do the weird thing like you don't have to dequeue and queue. With the stack, there's no such thing as a circular stack to optimize for memory. It's pretty simple in the sense that it works. In fact, let me show you this time the stack version first, or sorry, the array version first. So if I wanna, I wanna store a stack on my computer, I just make an array and I make the top point to the next available spot or to the currently used spot, which in the case of an empty stack would just be like -1. So if I want to insert to my stack, let's go ahead and bring in our helpers here. Actually, yeah, let's stick with the cubes. I was going to bring in the people, but let's do cubes now. Okay, so if I want to put something in the stack, I say push, get stored there. Put another one in, get stored there. Notice that I only keep track of the T for top. Could also be S for size, because that actually tells you the size, but then you have to do math, right? So you got +1 it. So yeah, that's basically how you put things in and then how you remove them. How you pop is you just see what the top is pointing to, take that out and move that. Now remember, when it comes to arrays, and I didn't mention this point in the queues because I kind of just assumed that but like when you remove something from an array, you're not deleting it per se, right? Particularly in this scenario here, like if I have something here and then I pop the 1, what is actually happening is T is going here. I'm couting, printing, whatever the square represents, but this is physically still here. We're just, think of it like it's deleted per se. Like think of it like a hard drive, right? When you delete something from a hard drive and it's not like a secure deletion, you're just marking that as available spot, but the data is still there. From a security perspective, be aware of that. When you delete a file and you put it in the recycle bin, and even after that you go and say delete permanently or whatever, the data is still in your hard drive and it can be accessed. The only time that data is going to truly be gone is if at some point I go in and I want to insert another square and I go +1 here, so it moves here, and now I can go in. Oh, I broke my square. Hold on. I move it here. I can go in and then overwrite that square with this one, and so this square goes away now because it's being overwritten. The same thing happens in the computer, okay? Only now, when I overwrite the data, is the data truly gone. At any point before that, I could have recovered the data, given it's not encrypted or something. And even if it's encrypted, if you know the decryption key, then you can still recover it. So I guess be aware of that from a security perspective. Always make sure you clean your hard drives before you sell them or something like that. So yeah, that's really how you do it when you're implementing it. You don't have to necessarily delete stuff from the array. Your T tells you what part of your array is valid and what part is not valid. The same works with the Q because of your front and back pointers or indices. If I have this scenario here where, my back is pointing to, actually, yeah, let's say it's pointing here. Okay, but this is what I actually have in there. What this really means is that this, and this are all invalid data. That, it's still stored, but it's not part of my queue because my back is pointing to the next available spot. So if I go in and bring a new storage item here, so I'm storing, I can't draw the stick figures. Let me just use my pre-existing one. If I want to bring a new one, he goes in there because that's the next available spot. And now this is overwritten by this. And this points there, which is the next available spot. Similarly here, if somebody gets out of the line, all that really happens is the F now points here instead of pointing to the 6. That data is still there. It's just, marked as empty. So it will get overwritten eventually when the circle goes around. So that's important, okay? It's important that you understand that. And it's also important because you got to make sure your indices are working correctly. Otherwise, you get invalid data. Like I said, you want to, even though I don't have it here as a function, nothing prevents you from coding like a print function that prints out the entire contents of a queue or a stack. And you got to make sure that when you do that, you don't print out the invalid data. You only print out the valid and contents of the stack or queue. So yeah, key point there. Okay, so with that said, again, if you max this out, so if you keep inserting into this and you eventually max it out, because of the awesome thing that you are only inserting at the at one side of this and you're not removing from that side, when you get full like this and you need to make a bigger one, it's a matter of just making that bigger one. So let's just, just make it +1 bigger. And that one you can just use a little for loop that does member copy. So like literally copies everything the same. And you will not run into any issues with this that you would have otherwise run into if you did this with a queue. And now you're literally all set to go now. So now you insert a brand new square. Okay, so that's cool. So but make sure you don't confuse them. With the queue, you have to do that magic. DQ, 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 and queue into the new one. With the stack, you don't want to do that. In fact, if you pop from the stack and then push into the new one, you're going to get things in reverse. Let's look at that actually. So if you're like, oh, let me just pop and push into the new one. So pop from the old one, push into the new one. Let me number this so you can see that happen. I'm going to pop, so it's going to pop the one at the top, push it into the new one, pop the next one, push it into the new one, pop, push, pop, push, pop, push. Look at that. It's reversed. So I guess that's one usage of a stack. If you want to just reverse things, you can using a stack. But not ideal, right? Not ideal here. So that's weird. What is being drawn there is not what I have, but now it is. Wait, no, it's not. I don't see the 1. Like, this is empty for me, and yet I see a 1 on there. That's scary. So, like, can I grab it? Oh, wow. Oh, now it appeared. Okay, that's scary. All right. The stack gods are not pleased that I was talking bad of them or something. Okay. So yeah, make sure that you do a normal for loop for a stack. Don't try to do the pop and push to be able to insert things. But there is a side benefit. If you ever want to reverse a list, just use a stack system to do that. That does actually remind me of another cool usage of a stack, and that is going to be your postfix notation. So you use a stack to evaluate postfix notation. You also use a stack for call stack for like function calls to be able to remember what the last context was. But that was a little fancy, so wait till 2.19 to understand it. But yeah, look up on your own if you want postfix. There's also prefix to look at too, but look at postfix first. It's a different way of doing math that avoids having to use parentheses, which of course allow you to work around order of operation. So there's no such thing as needing order of operation because everything is clear in the postfix notation. So some people really like it. So some engineers like really big fan of it. Dolly Jorgensen, one of our colleagues at UNLV, is a fan of it. So go up to her and talk to her about that. Like, hey, I heard you like postfix. So yeah, okay. So yeah, I think that's all I want to say about the array one. Let's just very quickly go into the linked list one, just to show you, and that way we can call it a day on this. So is there a wrong way to do the linked list one, or is it? Yeah, I guess there's a wrong way to do it as well. The wrong way is if you make that your top. So like if you make your tail now your top. In fact, maybe I should write that so you're not confused. You need a head pointer too, then technically. You know, if you want to pop out, you pop this out, but again, you have no easy way of moving this back without traversing the entire list, right? So just same problem as the Q1. So you don't want to do that. It's unnecessary. Instead, what you do is you make your head be your top. And that's it. If you want to push something into the stack, into the linked list stack, what you do is, so say you have this, and this is what you want to put in. So all you got to do is make that pointer point to the top, and then make that node be the new top. Bam, done. So you just keep popping, keep pushing in from that side. If you want to pop something out, which of course is going to be always what is at the top, it's just a matter of like taking this. Well, first of all, taking this data out, do whatever you want with it, and then moving that there. And then bam. Pretty straightforward, even easier to do than the queue. But both are pretty easy to do, especially if you're just if you're comfortable now with linked lists. If you're not, then you gotta get comfortable with that before you can do this. But once you are, you can. This is so much easier than doing like a sorted linked list or something like that. So yeah, that is it. So today we covered two new data structures, which may not be so new to you. Particularly the Q1, I'm pretty sure that you are familiar with them, but now at least we formally explain them to you. So, you know, implementing now for coding this should be a piece of cake. But I will show you that in the next video if you want to see some implementation in C++ of a stack or a queue. Okay, so but for this video, it's been long enough. So thank you all for watching, and I'll see you in the next one.